This is the first of 3 PowerPoint presentations covering telescopes. Prior to discussing telescopes, however, let me once again briefly mention Tycho Brahe. Recall that Tycho Brahe is perhaps the greatest observational astronomer to have lived prior to the invention of the telescope, and over the course of decades in the late 16th century, he very carefully charted or measured planetary positions in the sky. To do this with the level of accuracy that he was able to attain, which by far and away was the best at the time, only 8 arc minutes, you basically have to make your measurements using extremely large instruments. So when you measure angles on the sky with the naked eye, you then make these extremely large instruments such as this quadrant, as it's called, depicted here in this old painting. This quadrant here, as you can see, is quite large, and it was made out of steel. Basically, the larger the instrument, the more finely precise your measurements can be. Unfortunately, Tycho's instruments do not survive to this day. They were eventually melted down to make bullets. Okay, then using his own money, Tycho built his own private observatory on a small island off the coast of Denmark. The observatory does not survive to this day. It was referred to as Uraniborg. Okay, and then we get to the first telescopes. The first telescopes that were invented were refractor telescope. The refractor telescope uses 2 double convex converging lenses. The first lens is called the objective lens. This is right here at the front of the telescope, and you want to make this lens as large as possible. The reason why is because you want to gather as much light as possible. And then what I did here on this ray diagram is I depicted then what happens if you look at an extended object at infinity. So say looking at the moon. So we have light rays here, say, coming from the top of the moon, and these light rays are all parallel to each other, and they're on an angle here with respect to the optical axis. Those light rays then get focused right here to the focus of the objective lens, resulting in a real inverted image. However, this focal point right here is also the focal point for this lens right here that you actually look through. This is called the eyepiece. So the light rays then continue from this image constructed from the first lens. They then pass through the eyepiece like so, refract out the other side, and when they do refract, they refract parallel to each other. So then your eye is right here. Those light rays then are parallel to each other, so your eye is completely relaxed, and then therefore you're looking at an object that appears to be infinitely far away. Once again, the focus right here of both lenses is at this point. Okay, now you calculate the magnification for such a telescope in the following way. The incoming light rays here from the top of the moon, say, make an angle with respect to the optical axis. And then these light rays here that emerge from the eyepiece also make a different angle with respect to the optical axis. This angle here, however, is actually larger than this one here. And then you calculate the magnification here as this ratio. There are 2 big problems associated with refractor telescopes, however. The first problem has to do with what is called chromatic aberration. Recall that light begins to disperse into its component colors when it refracts through glass. This is unavoidable. So then therefore what you want to do is you want to make the focal length associated with the objective lens as large as possible. This then means that the telescope has to be extremely long. In addition to that, another problem associated with refractor telescopes is that all the weight of the telescope is right here at the front of the telescope where the large objective lens is. From an engineering standpoint, that is difficult to work with. So because of these problems associated with refractor telescopes, the largest refractor telescopes that have been built have only had an objective lens here with a diameter of 40 inches. I'll show you some pictures of that in just a few moments. Okay, before I do, however, right here is a nice picture of Galileo's refractors that he built in the early 17th century. His telescopes do survive to this day. They are currently housed in the Museum of the History of Science in Florence, Italy. Okay, this right here is the largest refractor telescope that's ever been built. The objective lens is here at the top of the barrel, and it has a width of 40 inches. You can see how long the telescope is. Once again, you want to make the focal length as long as possible. There is a duplicate telescope of this one here at the Lick Observatory near San Francisco. This particular refractor telescope is housed at an observatory in southern Wisconsin called Yerkes Observatory. It was built in the 1890s. And here is a photograph of Yerkes Observatory. It's currently a museum that's operated by the University of Chicago. It was also the last major observatory built at or near sea level. It's in southern Wisconsin, and it was the last major observatory built east of the Mississippi River. In the early 20th century, that's when we started to build observatories basically in the western portion of the country, which is drier. and we started to build them on top of mountaintops. You want to try and get above as much of the atmosphere as possible when making astronomical observations. Okay, now let's get to reflector telescopes. A reflector telescope uses a primary mirror, a parabolic concave mirror, to gather the light. Because you're using a mirror here to gather light, you do not suffer from the effects of chromatic aberration. In addition to that, from an engineering standpoint, all of the weight of a reflector telescope is down here at the bottom of the telescope as opposed to the top. So from an engineering standpoint, moving such a large telescope around is much easier to do. Okay, now on this ray diagram here, basically what happens is as follows. Once again, we have light rays coming in from an extended object at infinity, say the moon, and those light rays then here make an angle with respect to the optical axis. Those light rays coming in from infinity then form an image here in front of the mirror. This right here is a real inverted image that is at the focus then of this mirror. Now, most telescope designs, reflector telescopes designs, at this point here, they place a second mirror to either reflect the light rays back in this direction, like so, where you would then put an eyepiece here, for example, in the middle of the parabolic concave mirror. Usually a hole is positioned here. Or sometimes a secondary mirror is positioned here to redirect the light rays off to the side, like so. I've neglected to draw all of that on this diagram, however, for simplicity. So then therefore, basically what we have here is as follows. We have the light rays coming in from, say, the top of the moon like so, forming this image right here at the focus of the parabolic concave mirror. But then the eyepiece that you look through right here is a double convex converging lens. The focus of this eyepiece, this lens, is here. It's also at the same position of the focus of the parabolic concave mirror, such that when these light rays here then refract through this eyepiece, they refract out the other side parallel to each other, and then your eye is right over here. So because these light rays that enter your eye are parallel to each other, it's as if you're looking at an object that is infinitely far away. The angle that is made by these light rays here with respect to the optical axis is greater than this angle here. Once again, we calculate the magnification aspect ratio. Okay, now let me take you through the brief history of the construction of the largest reflector telescopes, continuing through this PowerPoint presentation and beyond. So this right here is the largest reflector telescope that was built in the 18th century by an important astronomer named William Herschel. William Herschel, for example, was the discoverer of the planet Uranus. The aperture, or size, of the parabolic concave mirror was 1.2 meters. You can see all of this scaffolding here that was necessary to steer the telescope around. The engineering of steering large telescopes around took a long time to figure out. This right here is the largest telescope that was built in the 19th century. It's referred to as Lord Rosse's Leviathan. Right here is the actual telescope itself. The aperture was 1.83 meters wide. It was an extremely difficult telescope to use, however, because they built this bizarre contraption here to try to steer it around, and that was difficult to do. In addition to that, it was built in England, where unfortunately the weather is usually pretty bad, so unfortunately the telescope was not easy to use. Okay, and then we get to the early 20th century, and that's when really modern telescopes really start to come into being. So this right here is one of the largest telescopes that was built early in the 20th century. This is the Hooker 100-inch telescope. It's at this point that we figured out the engineering that was necessary to mount extremely large instruments such as this. This telescope is at Mount Wilson Observatory, which is north of Pasadena. It is still in use today. The telescope today is now a National Historic Landmark. The reason why is because the American astronomer Edwin Hubble actually used this telescope to discover the expansion of the universe. Okay, here's a nice picture of Mount Wilson Observatory. Once again, it's just north of Pasadena. Even though it's fairly close to the light pollution of Los Angeles, it's still an important observatory in use today. Okay, the next largest telescope that was built after the 100-inch was twice as large. This is the 200-inch telescope. It was built at Palomar Mountain, which is east of San Diego. It was built in 1936. This would remain the largest telescope in the world for several decades. It is still in use today. Today, the telescope is operated by the University of California and by Caltech. Okay, so let me go ahead and conclude this here as part one of this screencast series on telescopes.